So what we're going to be starting to talk about today is steady state sinusoidal circuit analysis. So we are going to be looking at circuits that are excited by either a sinusoidal voltage source or a sinusoidal current source, and we are going to figure out how to analyze them. Okay, so before we get into this, I'm going to pick your brains / kind of explain something here. Okay, so if I have a DC voltage source connected to a resistor, what kind of voltage drop occurs across my resistor? A DC voltage drop, sure. So this is going to be VR and it'll be a DC quantity. What about the current flowing through my resistor? Also a DC quantity. What if I had a DC voltage source connected to a capacitor? My voltage drop going to be DC? Yeah, absolutely. What about my current? It's going to be 0, which is a DC quantity. And obviously the same thing would happen if I had a source, a DC source connected to an inductor. And as we have noticed in all of our circuit analysis, I can do any combination of resistors, capacitors, and inductors. And whenever they're connected to a DC source without any switching or anything that's introducing a transient, I get DC responses, right? So if I have DC excitation in, I get DC responses, so DC currents and voltages out. So let's look at what happens if I have an AC signal. Specifically, a signal where Vs of t in this case will be of the form Vm cosine omega t plus some phase angle theta v. Okay. So what would we expect the voltage drop across our resistor to look like? The exact same thing, because the resistor is in parallel with the voltage source, right? So VR of t would also be Vm cosine omega t plus theta v. What about IR of t? How do you think we'd figure that out? Exactly right. Good old Ohm's law. IR of t would simply be Vm divided by R multiplied by cosine omega t plus theta v. Let's look at this with a capacitor, and if we know how it works with a capacitor, we have a pretty good understanding of how it will work with an inductor as well, right? So if I have some capacitor C, this is my voltage Vc of t, and this is my voltage Ic of t. If Vs is of the same form, just a sinusoidal voltage, Obviously, VC will be the exact same thing because they are connected in parallel. IC is going to be C dV by dt, right? So that is going to look like negative omega C Vm cosine, sine omega t plus theta v. I don't know why my screen keeps moving on me, but it's driving me insane. And we could express that as a cosine function. And I'm going to leave the negative sign there because I don't want to do too many trig identities at the same time. Negative omega c Vm cosine omega t plus theta v minus 90 degrees, getting rid of my negative sign. This is going to look like omega c Vm cosine omega t plus theta v plus 90 degrees. So what I am trying to illustrate here is that in a situation where we have sinusoidal steady state, which means that our circuits have been sinusoidally excited for a very long time, the response to that sinusoidal excitation will itself be a sinusoid. That sinusoid will have the same frequency, right? So in all cases, we saw that for the capacitor, the resistor, and obviously for an inductor as well, our frequency of oscillations here is still omega, but our amplitude can be different and our phase angle can wind up being different. But we're going to have an excitation at that particular frequency, okay? So with that understanding, let's work a problem. So I have an AC voltage source. I will define its value in a moment. Connected in parallel to a resistor. This will be a 10 ohm resistor. And also connected in parallel to a 5 millifarad source. Excuse me, capacitor. Okay. Vs of t will be 12 cosine 15t plus 10 degrees volts. And our goal is to figure out what Is of t is, where I'm going to define Is of t as the source current leaving the positive polarity terminal. And my expectation here, based on what we just talked about, is that I will get a current of the form Im cosine 15t plus some phase angle theta I amps. So if I have a sinusoidal voltage in, I should get a sinusoidal current out. Okay. So how are we going to analyze this circuit? Anybody have any thoughts? What is the same thing that we always do? So what kind of circuit is this? It's a single node pair circuit because everything is in parallel. So what do we do when we have single node pair circuits? We apply Kirchhoff's current, okay? So I can say that Is of t will be equal to this current IR of t plus this current IC of t. Anybody have any problems with that whatsoever? Right. Okay. So IR of t is nothing more than Vs of t divided by R. So that's going to look like 12 cosine 15t plus 10 degrees volts divided by 10 ohms easily comes out to be 1.2 cosine 15t plus 10 degrees amps. Easy peasy. IC of t is C times the derivative of Vs of t with respect to time. So C is 5 millifarads, so I'm going to write that as 5 times 10 to the minus 3 amp seconds per volt. When I take the derivative of a cosine function, so the derivative of cosine omega t would be negative omega sine omega t. So I'm going to pull out a negative omega, so that's negative 15 per second. Then I'm going to have 12 sine 15t plus 10 degrees volts here. We can see that our volts cancel our volts, our per seconds cancels these seconds, and we're left with something in amps. And if I do the math, 5 times 10 to the minus 3 times negative 15 times 12 looks like negative 0.9. So negative 0.9 sine 15t plus 10 degrees amps. And I got to go to the next page. You guys caught up, or do you need me to wait a moment? All righty. So I'm just going to put these two results together, and I'm going to say that the current that I'm looking for, IS of t, is just those two things added together. So that's going to be 1.2 cosine 15t plus 10 degrees minus 0.9 cosine, sine 15t plus 10 degrees amps. So before class, I plotted these two functions on Desmos. So let me explain what our problem here is, I guess, before I show you the graphs, okay? So I'm expecting my source current to be a single sinusoid, right? So if I put a sinusoid in, I should get a sinusoid out. I have a combination of sinusoids right now. So the reason why I plotted this is because, so the red curve is the resistor current, the blue curve is the capacitor current. Well, if I add those two signals together, let me turn these off, it is a single sinusoid. So the question that I have now is, how do we take what we have mathematically determined and convert that into a single sinusoid? Yes. Let's go through things. So right now, it doesn't matter. I can add those two signals together, and it's just adding them point by point. So negative 0.9 sine 15t plus 10 degrees is going to be the exact same thing as positive 0.9 cosine 15t plus 100 degrees. They are literally the same thing. It's just looking at it from a slightly different perspective. So adding them point to point graphically changes nothing, whatever representation I have. Okay. We will wind up doing a conversion to a cosine in a little bit, though. All right, so what I'm going to do is I'm going to apply some of those pesky trig identities that we dealt with. Whatever, I guess that was Wednesday. Yeah. So if I use trig identity, I believe it was number 6. So that's when I have cosine alpha plus beta. So let me write the trig identities that I'm going to use. So cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. I'm going to make one small change. If I have a magnitude out front, that magnitude carries over here. Anybody have any problem with that? Okay. Another trig identity that we're going to use is the sine alpha plus beta one. That's how we're going to deal with the second half of this thing. So sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. And once again, if I have an amplitude out front, that amplitude gets distributed among my terms. Okay. So I'm going to use these two trig identities, and I can say that IS of t will be 1.2 times the cosine of 15t times the cosine of 10 degrees minus the sine of 15t sine of 10 degrees. And this is all the same line of math. 0.9 times the sine of 15t cosine 10 degrees plus cosine of 15t sine of 10 degrees. So that's just me using those two trig identities. And now I'm going to lump some things together, right? So I have a factor of 1.2 cosine 10 degrees and a factor of negative 0.9 sine 10 degrees that is being multiplied by cosine 15t. And then I'm going to have a minus sign for both of these factors, so I'm pulling the minus sign outside. So I'm going to have minus 1.2 sine 10 degrees is multiplied by sine 15t, and 0.9 cosine 10 degrees. This is also multiplied by sine 15t. And so now I can just evaluate parts of this in my calculator, right? Because 1.2 cosine 10 degrees minus 0.9 sine 10 degrees is literally just a number. That number happens, excuse me, happens to be 1.025. And then if I do the other part, 1.2 sine 10 degrees plus 0.9 cosine 10 degrees comes out to be 1.095. So we're going to have minus 1.095 sine 15. So things are slightly better in as much as we've somehow managed to get rid of phase angles, and now we only have a pure sine function and a pure cosine function combined together. So what we can do from here is use this trig identity backwards effectively to figure out what the A is, so what our magnitude is going to be, and what our angle is, right? So what I am saying is A cosine 15t plus some phase angle theta will be A cosine 15t cosine theta minus A sine 15t sine theta. Let me move this down one smidge here. No, I want to move it, not scale it. There we go. I'm moving it down because we can explicitly see that this 1.025 is A cosine theta. And this 1.095 must be A sine theta in the form that we have here using this trig identity. Allie, yes, ma'am.
So why are we doing?
Fantastic question. Okay. No, fantastic question. How do I make the sum of those two independent sinusoidal quantities? How do I get it in the form of a single sinusoid? Because I can look at this graph right here and see that this has a amplitude of 1.5 and some phase angle that is going to be, let's see, if I'm dealing with a cosine function, a little bit of a lag here, it looks like, right? Yes.
So why don't we just convert this sine to?
So let's look at some things here real quick. That's a fantastic question as well. So let me tell you why it doesn't work. Okay. So the question is, what would happen if we converted to a cosine function, the sine function to a cosine function from the jump? So that we'd have 1.2 cosine 15t plus 10 degrees. Let's call this minus 0.9 cosine 15t minus 80 degrees. Can I add those two together? No, because the phase angles are different. Right? I have to suffer if I'm working, let me rephrase that. If I'm choosing to work in the time domain, I have to suffer through these trig identities, okay? I'm intentionally being cryptic there because of what we're going to talk about in a moment. So, how do I figure out what A is, the amplitude of my resultant thing? So, A cosine theta squared plus A sine theta squared is equal to A squared cosine squared theta plus A squared sine squared theta, which is A squared times cosine squared theta plus sine squared theta, which we know that that is simply 1. So from that, we can say that our amplitude A is going to be the square root of A cosine theta squared plus A sine theta squared, or the square root of 1.025 squared plus 1.095 squared. Somebody throw that into your calculator. Tell me what we get. 1.5. So the magnitude that we just calculated using all these terrible trig identities exactly matches the magnitude that we have here. So we're on to something, okay? For our phase angle, we know that the tangent of theta is equal to the sine of theta over the cosine of theta, right? That's the definition of tangent. Does it change anything if I have a sine theta over a cosine theta? Absolutely not. So from here, we can say that theta is simply the inverse tangent of a sine theta over a cosine theta, which is going to be the inverse tangent of 1.095 over 1.025, which comes out to be 46.891 degrees. Okay. So using these two pieces of information, IS of t will be 1.5 cosine 15t plus 46.891 degrees amps. Let's check to see if we're right. So I'm just going to pop back over to Desmos, and I'm going to have a new thing here, and I'm just going to type in what we got. So 1.5 cosine 15x plus 46.891. So that is in degrees, and Desmos is set to be in radians. So I'm going to multiply that by pi divided by 180 degrees. And our two signals completely overlap each other. Okay. So we just worked a problem in the time domain. How did you guys feel about it? It's awful. It's absolutely terrible. It's garbage and we should never do it again. So let's talk about how we never do it again. Okay. One of the reasons why we'll never do that again, that was a whole bunch of work for a really simple circuit, right? If we added any other circuit element in there, the level of difficulty would be even harder. So let's circle back around to what Justin and Hannah were talking about here. Let's look at this representation. So I want you guys to put something in your calculator. Okay. If you have a Casio, put your calculator in complex mode for me. So we're just going to add, we'll really take the difference of two numbers here. So I want you to put 1.2 angle 10 degrees minus 0.9 angle negative 80 degrees. What did you get? What did you get? Okay, so tell me what the answer is in polar form. We'll circle back around to that in a moment because there's an issue with a sign there. 1.5 angle 46.89 or did I? Yeah, rounding error, okay? That is not a coincidence, okay? So complex numbers carry the same information as a sinusoid. They have a magnitude, a frequency, and a phase angle, okay? We are going to use the cosine representation for all of our sinusoids because that is the real part of an exponential complex number. Okay. So we could have skipped a ton of math when we got to literally this point by using the complex number representation of our currents and simply taking the difference there. Now, Allie, you had given me numbers in rectangular form. What were they again? Positive on both, right? So those are the numbers that we have right here, except that there was a sign difference for that part. That sign difference comes because there's a minus sign in that trig identity. The reason why I'm pointing that out to you, let's look at our homework. Come on, computer. So, homework number 19. Let's look at problem 1 here. Nope, that's the one that we were messing around with the last time. Let's delete all this jibber jabber. Okay. So we are given two sinusoidal functions. One is cosine 60, 100t minus 115 degrees. And then minus 39 sine 100t plus 87 degrees. And we are asked to find this as the sum of a pure cosine function plus the sum of a pure sine function, or as a single cosine function with a phase angle. So for this particular problem, instead of suffering through 2 pages of trig identities, we could say 60 angle negative 115 degrees minus 39 angle 87 minus 90 is negative 3 degrees is equal to 82.9105, so 9105. And then for our phase angle, I get negative 140.8575. Let's see what happens. I'll be damned. We got that correct without doing any trig identities whatsoever, but wait, it gets better. If I convert that answer from polar form into rectangular form, I get negative 64.3036. So I'm going to put that here as A, negative 64.3036. And then I get minus 52.3373. I need to flip the sign on the imaginary part because of that negative sign in the trig identity. So that's going to look like positive 52.3373. And boom, I've done that entire homework problem using complex numbers instead of sinusoids, and it takes me seconds instead of minutes. Okay. Complex numbers are your best freaking friends for steady state sinusoidal analysis. What we are going to find is that using complex numbers, all of our trig and calculus is replaced with algebra. Okay, so there's a wonderful, wonderful thing. So now let's explain why this black magic works the way it does. So if I have a linear black box network, meaning that it can contain any combination of resistors, capacitors, inductors. And I apply a signal. Let's call this signal X1. And I measure an output signal Y of 1. We should expect that if X1 of t is of the form Vm cosine omega t plus theta v, we found, actually, let's call this, let's not call it a voltage here because the voltage part doesn't matter. Xm cosine omega t plus theta x. We know that our output signal should be of the form Ym cosine omega t plus theta y. If we put a cosine function in, we should expect to get a cosine function out, and we just saw how that worked for that particular circuit, okay? Let's take that same linear black box network. We're going to put in a different input signal. This time it's going to be X2. And our response should in turn be Y2, right? Well, if X2 as a function of time is of the form Xm sine omega t plus theta x, what do you guys think Y2 is going to look like? So if we put a sine function in, we get a sine function out. Exactly right. How many of you guys remember the scaling property of linearity? We talked about way back in like lecture 6. So 6 weeks ago or something at this point. Anybody recall talking about that stuff? The scaling property of linearity stated that if we scale our input by an arbitrary time invariant factor, our output scales by the same arbitrary time invariant factor. So what if I scaled my input by a factor of j? It's an imaginary number, but it doesn't change with time or anything like that. My output should scale by the same thing. So now we're going to use the additivity principle of linearity and add those results together. So if I have my linear black box network and I apply some total signal x, where x of t is xm cosine omega t plus theta x plus j xm sine omega t plus theta x. My output signal, y. Actually, let me give myself some room here. Will be ym cosine omega t plus theta y plus j ym sine omega t plus theta y. So if you look at that list of trig identities that I gave you guys Wednesday, the 9th one was what I called Euler's identity. Euler's identity relates complex numbers to sinusoids, right? So xm cosine omega t plus theta x plus j xm sine omega t plus theta x is nothing more then the complex number xm e to the j omega t plus theta x, and this y of t in complex form is going to be nothing more than ym e to the j omega t plus theta y. Okay. What's really interesting about this, though, and this is why we get to use complex numbers to analyze sinusoidally varying circuits, is that the real part of our input gives us the real part of our output, which is what we're actually interested in, right? So the real part of our complex input is responsible for the real part of our complex output. So effectively, we can analyze a circuit using a complex number and then only take the real part at the output, and that will be the exact answer we're looking for, which is exactly what we noticed when we saw that our magnitudes were the same and our phase angles were the same when I had you guys plug it into your calculator using complex numbers. Okay. So using complex numbers makes it easier. Now let's figure out a formal procedure, okay? So electrical engineers are inherently lazy, myself included, and we want to make things as simple as possible. So what we have done is we have developed a kind of made up quantity called a phasor, okay? So if we have a signal V of t that is Vm cosine omega t plus some phase angle theta v, or a current signal I of t that is Im cosine omega t plus theta I. Using Euler's identity, we could say that V of t is just the real part of Vm e to the j omega t plus theta v. And I of t is the real part of Im e to the j omega t plus theta I, right? This is what we call the time domain. This is what I'm going to call the mixed domain. And electrical engineers like to work in the frequency domain, which is often referred to as the phasor domain, okay? So we represent time domain voltages and currents with a phasor representation, okay? So here is how we get our phasor representation, okay? So the phasor representation of our voltage is going to be V with a bar over it because it's going to be a complex number. And what I'm going to do is I'm going to take my magnitude, I'm going to take my phase angle, and I'm going to throw everything else away. I can do the exact same thing to find a phasor current. It's just the magnitude of the current and the phase angle of the current, sorry. Okay. So what we are doing here is we're really just saying, since we know that everything is going to be oscillating at that angular frequency of omega, we no longer have to care about omega because it's the same for everything. So it's just repeated information, and we'll see that in a moment. Okay. So I want to be very, very clear here. In order to get the phasor representation of any voltage or current signal, the time domain representation of that signal has to be with a cosine reference, okay? So, excuse me. So let's say that I have VA of t is equal to 10 cosine 15t plus 83 degrees volts. What would the phasor representation of this be? Angle 83 degrees volts. Absolutely. It does not need to be any harder than that. Okay, I'm going to make it harder than that, but it doesn't need to be really. All right. So let's say that we have VB of t is equal to 11 sine 6t plus 48 degrees volts. What is our phasor representation going to be? What was that? I disagree. Because this is a sine function and we need cosines, right? So be on the lookout for that, all right? So we would have 11, and then our angle would be whatever 48 minus 90 is, which is negative 42. And to be clear, we got that by saying that this is 11 cosine 6t of plus 48 degrees minus 90 degrees, or 48 minus 90, if my mental math is correct, is negative 42. Yes, ma'am.
You said the bar.
Just means it's a complex number. Yep. The hardest possible thing would be something like this, right? Let's say that we have 6 cosine 4 pi t plus 12 degrees plus 4 sine 4 pi t minus 20 degrees volts. Our phasor representation here. So the first thing that I would do is I would make this 6 cosine 4 pi t plus 12 plus 4 cosine 4 pi t minus 110. So that would look like 6 angle 12 plus 4 angle negative 110. And that's what's going to give me my phasor representation. So we simply just do that combination of sinusoids using complex numbers. So 6 angle 12 plus 4 angle negative 110 is 5.154 angle negative 29.160. Sorry, 29 degrees volts. Yes, ma'am. Absolutely. So adding or subtracting 90 degrees is giving you two things that are 180 degrees out of phase. So it doesn't matter if you add or subtract 180. It very much matters if you add or subtract 90. So you subtract 90 degrees to go from sine to cosine. You add 90 degrees to go from cosine to sine, which we'll never do, right? Plus or minus 180 is just getting rid of a negative sign. So that's why it doesn't matter which way we go. But to go from sine to cosine, subtract 90 degrees from the phase angle, which is trig identity number 2. All right, so this is how phasors work. Now let's derive some frequency or phasor domain relationships, okay? So let's start with a resistor. So let's say that I have some resistor R over which a voltage V of T drops and through which a current I of T flows. Let's say that V of T is a sinusoidal voltage. So Vm cosine omega T plus some phase angle theta V. And I of T is some sinusoidal current. Im cosine omega T plus theta I. And we know that these are the real parts of the complex representation, Vm e to the j omega T plus theta V. And the real part of Im e to the j omega T plus theta I. Okay, so Ohm's law tells us that V of T should be equal to I times R of T, right? So this is our generic relationship. This is good old Ohm's law. So if we use our complex representation here, we can say that Vm e to the j omega T plus theta V will be equal to R times Im e to the j omega T plus theta I. Okay. So what I'm going to do is I'm going to break my exponentials up. So this could be Vm e to the j omega T times e to the j theta V will be equal to R times Im e to the j omega T times e to the j theta I. And we can see that there's a common term of e to the j omega T on both sides. So we cancel those guys, eliminating that redundant information. And so we are effectively now in the phasor domain or the frequency domain, right? Because I have Vm e to the j theta V. Well, what's Vm e to the j theta V expressed as a polar form complex number? Vm angle theta V will be equal to R times Im angle theta I. And so I can see that my phasor voltage V is just equal to R times my phasor current I. So Ohm's law is just Ohm's law, even in the frequency domain, which makes a lot of sense. We can infer a couple of other things here that are pretty important, okay? So let's look at this representation right here, and we'll come off and do a little aside, all right? So we can see that we have a exponential form complex number on the left-hand side and an exponential form complex number on the right-hand side, which means the magnitude of the left-hand side has to equal the magnitude of the right-hand side, and the phase angle of the left-hand side has to equal the phase angle of the right-hand side. So by that, I mean that Vm will be equal to just R times Im, and theta V must be equal to theta I. What this tells us is that resistors do not introduce a phase shift. Okay. So the current and the voltage through a resistor will have the same phase angle. Always, always, always. The current and the voltage through a resistor will have the same phase angle. So theta V will be equal to theta I. Now, let's look at inductors. So let's say that I have some inductance L. over which a voltage drop V, let's just call it V, occurs, and a current I flows through it. V of t will be the same thing that we had before, Vm cosine omega t plus theta V, which looks like the real part of Vm e to the j omega t plus theta V. I of t will be a sinusoidally varying current, so Im cosine omega t plus theta I, which is the real part of Im e to the j omega t plus theta I. The voltage drop across an inductor is equal to L di by dt. And so if we use our complex representations here, that's going to give us Vm e to the j omega t plus theta V will be equal to L times the derivative of Im e to the j omega t plus theta I. So what's going to happen when I take the derivative here? Sorry, what? Not just omega. Omega is coming down, but there's also going to be a j that comes down, right? So taking the derivative in the time domain is effectively multiplying by j omega in the frequency domain, right? So this is going to be j omega L times Im e to the j omega t plus theta I. I'm going to break up my exponentials again. So I'm going to have Vm e to the j omega t e to the j theta V will be equal to j omega L Im e to the j omega t e to the j theta I, and my j omega t parts away. So this is going to look like Vm angle theta V as a polar form complex number will be equal to j omega L times Im angle theta I as a polar form complex number, or phasor voltage V is equal to j omega L times phasor current I. Now we're going to go back up a step here and we're going to play around with things as well. Okay. So on the right hand side, let me explain exactly what I'm looking at here. So I'm looking at this piece right here. So I have j times omega L Im e to the j theta I. Okay. So effectively, I have a rectangular form complex number j omega L being multiplied by a polar form complex number. So what we're going to do here is we're going to convert into all polar or exponential form complex number. So this is a quick aside here. I'm going to draw a complex plane. Here is our positive real axis, and here is our imaginary axis. So let's say that I went out 1 unit in the real direction as a rectangular form complex number. That looks like 1 plus j0, okay? As an exponential form complex number, that looks like e to the j 0 degrees. And as a polar form complex number, this looks like 1 angle 0 degrees. What if I went out 1 unit in the imaginary direction? That's going to look like 0 plus J1, or 1 e to the j 90 degrees, or 1 angle 90 degrees. If I go 1 unit in the negative real direction, that's -1 plus J0, or 1 e to the plus or minus j 180, or 1 angle plus or minus 180 degrees. And finally, if I go 1 unit in the negative imaginary direction, that looks like 0 minus J1, or 1 e to the minus j 90 degrees, or 1 angle negative 90 degrees. So when I have a j by itself, like I have right here, that's the same thing as me having omega L Im e to the j theta I e to the j 90 degrees. I can lump those two exponentials together as e to the j theta I plus 90 degrees, like this. So what this tells me is that the magnitude of my voltage is just equal to omega L times the magnitude of my current, and that theta V is theta I plus 90 degrees. What does this mean? The voltage, or the phase angle of the voltage, is always 90 degrees more positive than the phase angle of the current. So in an inductor, the current will always lag the voltage. So these are our phasor relationships for inductors. And unless anybody has an objection, let's go ahead and move on to capacitors. So for a capacitor, where here's our voltage, here's our current. I'm not going to write down the voltage and current again because it's just using the exact same sinusoidal thing that we've been doing. We know that the current through the capacitor is equal to C times the derivative of the voltage, right? So we could say that Im e to the j omega t plus theta I will be equal to, so what did we do when we took the derivative earlier? We multiplied by j omega, right? J omega c Vm e to the j omega t plus theta v. Since there's a common factor of e to the j omega t on both sides, this is going to look like Im e to the j theta I is equal to j omega c times Vm e to the j theta v, which we could say is the same as omega c Vm e to the j theta v plus 90 degrees, using the same identity that we used a moment ago. So we have Im angle theta I will be equal to j omega c times Vm angle theta v, or phasor current I is equal to j omega c times phasor voltage V. So that's our general relationship for current and voltage in a capacitor. looking at this guy, we can see that the magnitude of the voltage is going to be Im over omega c. And we can also see that theta v will be theta I minus 90 degrees. Which means in a capacitor, our current leads our voltage by 90 degrees. Always, always, always. Okay, so we are almost ready to analyze these circuits in the simplest possible way we can. We literally have one more thing to produce here, okay? So we have these phasor relationships, relating phasor currents and phasor voltages in resistors, capacitors, and inductors. So the last thing that we are going to talk about today is the concept of impedance, okay? So let me go to a new page here. So in a DC circuit, if I have a linear network and I excite said linear network, if I measure the voltage across the terminals of the network and I measure the current flowing into the network, we found that resistance was simply the ratio of voltage to current. And I made you guys literally do an experiment just like this on the second day of class. Or maybe it was the third day of class because I talked too much the second day of class. But anyway, there is a similar thing in AC circuits. So in an AC circuit or a steady state sinusoidal circuit, if we have our network and we sinusoidally excite it, does not matter if we use a voltage source or a current source. If we measure the phasor voltage across the terminals of the network and we measure the phasor current flowing into the network, what we get is Z, the impedance, which is defined to be the ratio of the phasor voltage divided by the phasor current. Our impedance Z will be a complex number because it is a ratio of complex numbers, right? So let's look at it in polar form first. So that's going to be Vm angle theta V divided by Im angle theta I, which is just the magnitude of our voltage divided by the magnitude of our current with an angle of theta V minus theta I, or magnitude of Z angle theta Z. That's our polar form representation. Okay. Nothing more than the ratio of voltage over current, just like resistance was. Okay. Now, because it's a complex number, we can also represent it in a rectangular form, right? So in rectangular form, this is going to be the magnitude of Z cosine theta Z plus J, the magnitude of Z sine theta Z, which is R plus JX, where R the resistance is the real part of impedance, and X the reactance is the imaginary part of an impedance. So I want us to find the impedances of resistors, capacitors, and inductors based on these relationships, right? So for a resistor, the impedance ZR is by definition the ratio of the phasor voltage to the phasor current. So you guys go back a page in your notes and tell me what that's going to be. Annie, what do you think it is? You're looking at notes. So we had phasor voltage V is equal to R times phasor current I. So divide both sides by phasor current I. What do we get? R. Absolutely right. The impedance of a resistor is nothing more than the resistor value, okay? In a more formal rectangular form description, that's going to be R plus J0. And in a polar form, that will be R angle 0 degrees. So what are the units of resistance? Ohms. So the impedance of a resistor is measured in ohms. I'm going to put here rectangular and over here polar. All right. Now let's look at an inductor. So the impedance of an inductor will be the ratio of the phasor voltage drop across the inductor divided by the phasor current flowing through the inductor. Somebody do the algebra and tell me what this is going to be. J omega L. More formally in rectangular form, this is going to look like 0 plus J omega L, or in polar form, omega L angle positive 90 degrees. What are the units here? Okay, so omega is measured in radians per second. So we have 1/seconds. Inductance is measured in henries, where a henry is a volt second per ampere. If my stylus will write, that would be helpful. Seconds cancel seconds, so we have volts per amp. What's a volt per amp again? An ohm. So the impedance of an inductance is measured in ohms as well. Now we'll deal with capacitances. So the impedance of a capacitor is the ratio of the phasor voltage divided by the phasor current by definition. Somebody do the algebra and tell me what this is going to be. Got something for me, Jackson? 1/J omega C. Absolutely correct. Okay. So more formally, this is going to look like 0 minus J over omega C. So let's talk about this because that's not obvious. I'll do that down here, right? So 1/J, if I multiply that by J over J, looks like J over J squared or negative J. Okay, so I'm putting it in this form specifically because we should always consider capacitances to have negative reactances. Inductors will have positive reactances, okay? In polar form, this becomes, 1 over omega c with an angle of negative 90 degrees. And our units here are going to be 1 over per second. The units of capacitance is the farad. The farad is an amp second per volt. So these seconds cancels out and we have 1 over amps per volt, which is the same as a volt per amp or an ohm. So the impedance of capacitors is also measured in ohms. So what is a benefit of the impedances all having the same units? Now, in the steady state sinusoidal domain, resistors, capacitors, and inductors are all impedances, and so they can all be combined together just like we did with resistors, okay? So there are no longer special rules for combining capacitors and special rules for combining inductors. Everything combines just like a resistance does. So let's put this together and reanalyze the circuit we did at the very beginning of the class. Okay. So here is our time domain voltage. Here is our 10 ohm resistor. Here is our 5 millifarad capacitor. We're trying to find this quantity Is of t, where Vs was 12 cosine 15t plus 10 degrees. So we know, and we're trying to find Is of t. We know that working this problem in the time domain is terrible and a waste of time. So we are not going to do it. Instead, we are going to convert this circuit from the time domain to the frequency domain. So that means we're going to replace all of our voltages and currents with their phasor representation, and we're going to replace all of our resistors, capacitors, and inductors with their impedance, okay? So what is the phasor representation of my source voltage? (12∠10), absolutely right. Because we're given a cosine function, we take the magnitude, we take the phase angle, and we throw everything else away, okay? So 12∠10 degrees volts. What is the impedance of our resistor? 10, because the impedance of a resistor is just the resistor value itself. What is the impedance of our capacitor going to be? So recall, the impedance of a capacitor is 1 over j omega c. So that's going to look like 1 over j times 15 times 5 times 10 to the minus 3. So negative j 40/3 of an ohm. We're now trying to find our phasor current Is. So how would we do it? So I would argue that Is is just 12∠10 degrees volts divided by 10 ohms times negative j 40/3 of an ohm over 10 minus J 40/3 of an ohm, because I'm just treating those two impedances like they're in parallel because they're impedances in parallel. And if I put this into my calculator, 12 angle 10 divided by 10 times negative 40 thirds I over 10 minus 40 thirds I think that's I'll find that in a second. I get 1.5 angle 46.8698. So let's call that 870 degrees amps. So IS of T is 1.5 cosine 15T plus 46.870 degrees amps. So if we understand how to convert from the time domain to the frequency domain, meaning we understand how to represent voltages and currents as phasors, and how to represent resistors, capacitors, and inductors as impedances, we can just do DC circuit analysis techniques using complex numbers to solve any problem that I can throw at you guys. So this third section of the class, from this point, the analysis is literally nothing new whatsoever. We're just using complex numbers. Okay. So KCL, KVL, Ohm's law, current division, voltage division, source transformation, source combination, superposition, all of those things are fair game for circuit analysis techniques. Technically, nodal analysis and mesh analysis are as well. I want to warn you, none of the calculators that you're able to use in this class is capable of solving a system of complex numbers, okay? So we are going to fall back on the basics in order to avoid using nodal and mesh, okay? So over the next couple of class meetings, like I would like to know what of our DC circuit analysis techniques you guys would like a refresher on. And then I will focus on working problems to remind you of how all that stuff works. What the hell did I just do? Okay, so what don't you guys remember? Current and voltage division. All right, I'm gonna write that down. Okay. The superposition. What else? We got 2 class meetings to fill up with this stuff. Technically, we have a lab on next Wednesday, I think, but yeah. KCL, KVL, Ohm's law, current division, voltage division, source transformation, source combination, superposition, Thevenin and Norton equivalent circuits. Yeah, pretty much. And mesh and nodal also are fair game. It's just our calculators can't do it. So we wouldn't do a Thevenin resistance, we do a Thevenin impedance. Yeah. Yeah, it's the same thing. It's all the same thing. That's what I'm trying to burn into you guys' brain. You guys come into this third section of class and everybody's freaking out because they hear about how hard it is. It's not. It's the same damn thing you did for the first third of the class, except there are complex numbers. You just can't rely on mesh as a crutch, and that's what pisses you guys off. Yes. Sure. Yeah. So I'll throw KVL and KCL on here as well. All right. Just teach the whole class again. Okay. So what I'll likely do is I'll come up with a couple of example problems and then we'll approach them from different ways because it's really going to be whatever is you're most comfortable with is the way that you should do it. Okay. But I'll show you how you can use Thevenin and Norton equivalent circuits to simplify things so that you don't have to use nodal and mesh and things like that as well. All right, so I have talked for a solid 90 minutes, so I'm going to stop talking. You guys have an in-class assignment. Go crazy.